So, History of Math, lecture 4, and we are finishing chapter 2, which is on Euclid's proof of the Pythagorean theorem. And William Dunham, the author of our text, makes a very important and very simple but somewhat surprising point, which is that Pythagorean theorem itself is very surprising. So let me draw a right triangle. So this is a right triangle with this as the right angle. And we label the vertices A, B, and C. And Euclid and the Greeks think about everything geometrically. So on each side of the right triangle, they construct a square. So let me try to do that. So the square on the hypotenuse let's see, is that about right? Yeah, approximately. So this is a square. Let me label this D and E. So this is the square on the hypotenuse. And let me also construct the squares on the two legs. Fortunately, I have a piece of plastic which has a right angle, so it's a little bit easier. So this is the square on one of the legs. This is K and H is here. And then I need the square on the other leg. And let's call this F and G. So we have squares. Here's a square. Here's a square. And here is a square. And somehow we want to prove that the area of this orange square is the same as the sum of the areas of the two small squares. So that's the Pythagorean theorem. And the beautiful, brilliant way that Euclid proved this result was to draw an auxiliary line. You might say, how did he think of it? Well, we have no idea how he thought of it, but he thought of it, or someone thought of it. And the line is the vertical line from A perpendicular to the hypotenuse and down through this orange square. So let me draw that line. So there's no reason why Euclid should have thought of this, but he did. So you draw this vertical line. It's the line perpendicular to the hypotenuse. And the hypotenuse, this is a square, so BC and DE are parallel. So this line is also perpendicular to the base. And let's label these points M and L. And what we're going to, so the area of the square at the bottom, BCDE, or if I go around, well, BCED is the sum of the areas of two rectangles. Here's one. And here's the other. So the area of this big square is the sum of the area of the green rectangle, BMLD, plus the area of the orange rectangle, MCEL. So this one is orange. And this one is green. Okay. Any questions about that? And what we're going to prove is that the area of the square, let me make it in green, the area of the square ABFG equals the area of the green rectangle. BMLD. And we'll also prove the area of the square on the other side of the right triangle, ACKH,
AC is equal to MCEL,
equals
the
the
area of the
area of the
rectangle.
rectangle at the bottom. MCEL. So that's the idea of the proof. We want to prove this big square has the same area as the two small squares. And by a miracle, we're able to divide the square, the big square at the bottom, into two rectangles. And the green rectangle, the left side, is equal to the area, has the same area as the green square. And this orangish rectangle on the right side has the same area as the other square. Okay. So that's what we're going to do. This is the fundamental picture. And the way we do that is very clever. So we draw. So we're going to do, so, and these two parts are done separately. So this is, if you like, part one, and this is part two. So what is the proof of part one? That's the green square has the same area as the green rectangle. So we draw two more lines. We draw the line from C to F, and we draw the line from A to D. Okay. So we have a picture that's getting more and more complicated. But for the moment, we don't have to draw, we're not going to draw any more lines, right? In order to prove part one, we have everything we need. Now, we do know something about areas of squares and areas of rectangles and areas of triangles and the relations between them. So the proof of the Pythagorean theorem and what's slightly less well known, the converse of the Pythagorean theorem, are the last two theorems in the first book of Euclid's Elements. The Elements consisted of 10 or 12 books. Some of them were missing and disappeared over the course of thousands of years. But in book one, the last theorems have to do with the Pythagorean theorem and its converse. And Euclid can make use of results he already proved about triangles and squares. And one result is the following. Let's look at triangle, the skinny triangle. We have triangle ABD, right? That's this triangle. And let's also look at this other skinny triangle, triangle FBC. And we're going to prove these two triangles are congruent. Congruent triangles. So the first thing we're going to do is prove that these are congruent triangles. Now, Euclid had already proven various ways to tell that two triangles were congruent. So, for example, if you have a triangle ABC and a triangle DEF, and there is something called SAS, side angle side. So if the side AB has the same length as the side DE, and if this second side AC has the same length as this second side DF, and if this angle let me call it alpha and beta, if the angle alpha, this just means angle, equals the angle beta. So here we have equal sides, and here we have equal angles. So we have two sides and the angle between them of one triangle are equal correspondingly to two sides and the angle between them in the other triangle. So side angle side. If that happens, then the two triangles are congruent. So this is one of the classical theorems in geometry about how you determine, how you can prove two triangles are congruent. Congruent means, among other things, that you can imagine if you picked up the triangle, the first, and put it on the second, it would cover it perfectly. Nothing left over or sticking out from either one. So that is side angle side. There's a second way, a second theorem that says when triangles are congruent. It's called SSS. So this is side, side, side. If all three sides of the triangles are the same, so AB has the same length as DE, AC has the same length as DF. We're not saying anything about the angles, but the third sides, BC and EF, are equal, have the same length. Then again, the triangles are congruent. We also have angle side angle. So in this case, let's say angle alpha, this angle, equals angle beta. Let's call this angle beta. Let's call this angle gamma, and this angle delta. Angle gamma is equal to angle delta. And the side between those two angles are the same for both triangles. So AB equals DE in length. So this is angle side angle. Again, that's a third condition for triangles to be equal. And there's a fourth, which is angle, angle, side. Angle, angle, side. So suppose angle alpha equals angle beta, angle gamma equals angle delta, and not necessarily the side between the angles, but one of the other sides, say AC is equal to DF, then again, those triangles are congruent. So these are four theorems, four different theorems in Euclid. Four theorems that give us ways to determine if two triangles are congruent. So let's go back and look at our picture. I want to show that this narrow triangle, ABD, is congruent to the narrow triangle, FBC. I mean, they kind of look congruent, but that's not a proof of anything. So what can we say? Well, in this triangle ABD, the side AB is one side of this square. All four sides of a square are equal, so AB has the same length as FB. So this side of one triangle is the same length as this side. Now, again, if you look at, we have a square here, BCED. The side BD is one side of the square, and BC is another side of the square. BD and BC have the same lengths. Let me draw just another picture of these. So I have this triangle. I'm going to just separate them. So this is A, B, D. And this triangle is B, F, C. There's this triangle and this triangle. And I just said that AB and FB are sides of a square, so they have the same length. And BD and BC are sides of a square, so they have the same length. AB equals BF, BD equals BC. And what about the angle between them? If the angle ABD is the same as the angle FBC, then triangle ABD is congruent to triangle FBC by side angle side, right? Side angle side, side angle side. So what is this angle ABD? So let me sort of blow that up for a second. My picture looks like this. This is the angle ABD, and perpendicular to that is this line, BMC. This is a right angle. And this is angle ABD. So angle ABD consists of this part plus a right angle. But what about angle FBC? If you look at the picture, FB is perpendicular to BA. So if I look at that picture, the angle...
Professor? Sorry, I was gonna ask, could you move the paper over a little, please? Thank you.
Right. So this was the angle ABD. And I have a line perpendicular to BD. That's the hypotenuse of the triangle. So angle ABD is the sum of this green angle, angle ABC, plus this, plus a right angle. And the other angle I'm interested in, which is angle FBC, that's this angle. That's equal to this, which is a right angle, plus the green angle. So the two angles are equal, right? This is a right angle plus the green. This is a right angle plus the green. These angles are equal. Therefore, these triangles are congruent by side angle side. So what I just proved is that these skinny triangles are congruent. Right? So this is an important point, and again, it's discussed very carefully and legibly in the text. This is just the first step. Right? The first step is that the skinny triangles are congruent.
Professor, can I please see the other page that you had?
This one.
Yeah.
Sure.
So you had, for the ones where they have two right angle, you had two angles that you proved. And can you so you stated that you proved this by side angle side, correct?
No. Oh, I proved
okay.
I proved the triangles are congruent by side angle side.
Right.
To prove
okay.
the triangles are congruent by side angle side, I have to know that the corresponding angles in the triangle are equal. So I have this angle. I'm drawing it in blue now. So in this triangle, I have the angle ABD. In this triangle, I have the angle FBC. And I need to show the blue angles are congruent, are equal. And the blue angles, here's one of them. It consists of the green angle plus a right angle. And the other angle, maybe I should use a different color. This angle, and I have this angle. And this red angle also consists of the green angle plus this, which is a right angle. So that's the proof that the two angles are equal, and the corresponding sides next to those angles are equal. So by side angle side, the triangles are congruent.
Okay, got it. Thank you.
Now,
and we know that these angles, like without the green angle, are right angles because
well, we drew squares.
Oh, okay.
This is a square.
Okay.
All the angles in a square are right angles.
Mm-hmm.
So these are all we have right angles all over the place. These are all right angles. Okay. Now, let me again take another part of this picture. So I have this green rectangle at the bottom. Looks like that. And I have, so this is A, B, D, L, and M, right? So from this picture, this is the green rectangle at the bottom, and this is that skinny triangle ABD. Okay. Let me just draw the picture horizontally. It might be a little bit clearer. So I have this rectangle, and I'm just turning this diagram around. This is LM. The top is DB. And this line LM extends to A. And I have a line, I have my triangle, which goes from D to A. Right? So this is all the same picture. I'm just drawing it over and over and over again. This is this green rectangle. And here, it's kind of sloppy, but this is my triangle. And if you have read the chapter as you're supposed to do, preferably even before the lecture on the chapter begins, on page 46, there is proposition Roman numeral 1.41, which says if a parallelogram has the same let's see. Actually, this picture I started with is actually the one I want to look at. Let me just draw that again. So this is proposition Roman numeral 1, book 1, proposition 41. If a parallelogram has the same base as a triangle, so this is the picture that you find in the text. So here's a parallelogram. AB, this is the base. And if you have a triangle which has the same base as the parallelogram, and if you imagine the line through the top of the parallelogram, DE, extended, and there's some point on that line which is so you have a parallelogram and a triangle. The parallelogram is ABDE. That's the parallelogram in blue outline. and we have a red triangle with the same base as the parallelogram, and the height of the triangle and the height of the parallelogram are the same. The way you would say that, a way to say that geometrically is, if you take the line through the top of the parallelogram, DE, the third vertex of the triangle lies on that line. So if a parallelogram has the same base as a triangle, and the way it's stated in Euclid and in the book is, and be in the same parallels. Here's a parallel, here's a parallel. In other words, the way we might say it is, have the same height. Then the area of the parallelogram is equal to twice the area of the triangle. Now, again, you know this before you've seen it in Euclid, because they teach you somewhere in school the area of a parallelogram is the base times the height. And they teach you that the area of a triangle is half the base times the height. So if the triangle and the parallelogram have the same base and the same height, the area of the parallelogram is twice the area of the triangle. Right? So this is something you know. And now let's go back to our basic picture for the Pythagorean theorem. I have let's see. Here's my picture. Let me rotate it so it looks like this, if you don't mind. So here is the triangle, here is the rectangle. BDLM. That's this green rectangle. And I take this line ML, which is parallel to BD, and extend it. And on that line is this point A. So I also have the triangle ABDL. So if you look at this picture, the triangle ABD, and in this case, it's actually a rectangle. The rectangle BDLM have the same base. The base of the triangle and the base of the rectangle are both this line BD. And the height of the triangle and the height of the rectangle are the same. Have the same height. So therefore, the area of this rectangle, the green rectangle, BDLM, is 2 times the area of the triangle ABD. Okay. So if we come back to our picture, I have this green rectangle, this tall, skinny rectangle, and I have the triangle ABD. They have the same base and the same height, so the area of the rectangle is 2 times the area of the triangle. Now, let me turn this picture again a little bit. I also have this small square and this triangle. So let's see. How should I draw that? So this is F B A G. That's the second green square. And if I extend this AG, that's the parallel, some point, this line through G and A hits this point C. And I have the triangle FBC.
Professor, can you please put the paper up a little?
Right.
Thanks.
So all I've done is redraw this part of the diagram. So I have my main picture. I just rotated, so I'm looking at this as the way I'm drawing it is I'm making this side of the square parallel to the bottom of the paper. I have this square and this triangle. And again, if you look at this, the triangle FBC and the square FBAG have the same base. And the same height. Because the height of this triangle from here to here, these two parallel lines. So therefore, the area of the square ABFG, like that, equals 2 times the area of the triangle FBC. Well, that's really very good because the area of the green square is twice the area of this triangle. The area of the green rectangle is twice the area of this triangle, right? So the area of the green square is twice the area of this triangle. The area of the green rectangle is twice the area of a different triangle. But those two triangles are congruent. So they have the same areas. So the square and the rectangle have the same areas. So we get our big conclusion, which is what we wanted to prove. The area of the square, ABFG, equals the area of the rectangle, BMLD. It is. This little square on one leg of the right triangle has the same area as the square of this rectangle. And in a very similar way, which I asked you to try and to figure out if you can in one of the homework problems, you can show the area of this orange square has the same area as the orange rectangle. And that is Euclid's proof of the Pythagorean theorem. It's not a slick little algebra proof like I showed on Monday. It's a pure geometric argument. And really, you need to spend a lot of time studying this because, as I keep saying, in each chapter, the most important thing to learn are the proofs of the great theorems. There's one great theorem in every chapter, and you really need to understand it and how to prove it. Now, what is also in the chapter as part of the great theorem is a converse. So let's keep looking at this picture. Here's my right triangle. And on each side of the right triangle, I built a square. And I proved, this is the Pythagorean theorem, the sum of the areas of the two small squares is equal to the area of the big square. So in Euclid, book 1, this is proposition 147. It's the next to the last proposition in the first book of Euclid. And the last proposition, which is, if number 47 is next to last, the last one has to be number 48. It says, if you have a triangle, let me just draw it like this. Right? And if on each side of the triangle, you construct a square, so let's say this is A, B, C. So let me just write it like this. If the area of the square on AB, I'll just write it like that, and the area of the square on AC, which is AC squared, is equal to the area of the square on the side BC, then angle A is a right angle. Then you have a right triangle. So if you know that this plus this equals this, then you have a right triangle. Right? Angle A or angle BAC. Right? So this is the opposite. This is the converse of the Pythagorean theorem. So let me give the proof. So let's say this is triangle ABC. And I'm not going to assume that this is a right triangle, but I do know that the square on AB plus the square on BC equals, the square on AB plus the square on AC equals the square on BC. Okay, now, what do? We construct a line segment EA perpendicular to AC. So there's a proposition in Euclid that says, given a line segment and a point at the end, you can construct a line perpendicular to it. That is, given a line and a point on the line, you can always construct a line perpendicular to that. So this is some line AE. And given a line segment, on any other line, you can construct a line segment the same length as that line segment. So this is step one. Construct this perpendicular. Step two, construct the point D on the line AE such that AE and AB have the same length. So I have this line AB, which is part of my triangle. I can find a point D on this line. Let's see, probably over there, such that AD and AB have the same length, right? And we know this is a right angle. So if I look at this triangle, that's a right triangle. So triangle DAC is a right triangle. So by the Pythagorean theorem, since this is a right triangle, the square on the hypotenuse is equal to the sum of the squares of the legs. On the other hand, our hypothesis from which we started is that for this triangle, that's the triangle we started with, AB squared plus AC squared equals BC squared. So AD squared, AD is the same as AB, so this is the same as AB squared plus AC squared, and that's equal to BC squared. That was our hypothesis. So the triangle on CD has the same area as the triangle on BC. So therefore, the length of CD equals the length of BC. So CD and BC have the same length. We constructed AD to have the same length as AB. By construction. And finally, everything is equal to itself. The length of AC equals the length of AC. So if you compare these two triangles, corresponding sides are equal. So by side, 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 triangle DAC is congruent to triangle BAC, which means corresponding angles are equal. Angle DAC equals angle BAC, but this by construction is a right angle. So this angle is a right angle, And so triangle BAC is a right triangle. That's it. End of the proof. Now, I know that in many schools in New York and elsewhere, they teach very little to no geometry. It used to be everyone in America had to study geometry in the 10th grade. So if you haven't studied geometry before, these kinds of arguments may be new to you, which just means you have to spend a lot of time going through these arguments step by step, sentence by sentence, line by line, word by word, to understand the kind of reasoning. Because this is one of the most important things in the history of mathematics. It's not just the geometry in itself, but what is often called the axiomatic method, where you start from a certain axioms or postulates and you draw conclusions from them by logical rules of inference, by doing mathematics. And if you take higher level math classes beyond calculus, typically, you do have to prove stuff. And the proof method originates with the Greeks. There is mathematics in Egypt and Babylonia. There's mathematics in China and India. There is mathematics in Central and South America, much of which disappeared because of the impermanence of the records, the materials on which things were written down. But as far as we know, there is no axiomatic method used in any of those mathematical cultures. The first place we see this kind of reasoning is in the Greeks from about 300 BC and even earlier. Alexander the Great and Euclid were contemporaries. And it's really important. So I certainly encourage you to spend a lot of time studying these arguments. Now, one thing we have not proven yet are theorems, which again, you use all the time, certainly in calculus, which says, if you have a triangle, ABC, the sum of the three interior angles of a triangle, in high school, you might have said is 180 degrees, or once you learn a better way of measuring angles is pi radians, or what the Greeks would say is 2 right angles. Or 180 degrees, or pi radians. However you want to measure it, we never prove this. And the proof requires something which is one of the the fifth of the 5 postulates in Euclid, and we haven't used it yet. In fact, Euclid defers using it until book 2. Remember, postulate 5 in Euclid said the following: if you have 2 lines, and if a third line crosses them, so you have 4 interior angles. If you take 2 interior angles on the same side, if alpha plus beta, if the sum of two interior angles on the same side of one line crossing 2 others is less than 2 right angles, then for this line L1 and L2, then L1 and L2 eventually intersect. If you carry them out far enough, somewhere out there, they're going to intersect. Or in other words, L1 and L2 are not parallel. Now, many people, the Greeks and many people for 2,000 years afterwards, thought this was more like a theorem than a postulate. And one thought that it should be able to prove this just using everything else from plane geometry. So there was the following question: is this postulate 5, which we can call the parallel postulate, provable from the rest of geometry? I mean, could we actually prove this and not have to assume it when we started? For example, and no one knew. No one knew. That's really the hard question. And in order to prove the sum of the angles of a triangle is 2 right angles, you need to use this. So an equivalent form of postulate 5, which is sometimes called, there's a guy named Playfair. The British used to have funny names like that. Playfair. This is called Playfair's postulate. Said, given any line L and any point P, there exists one and only one line through P parallel to L. That's Playfair's postulate. And this is the form of the Hilbert's of Euclid's fifth postulate you've probably heard of. Given a line and a point not on the line, there's always one and only one that is a unique line through the point parallel to L. So let's apply that to our triangle A, B, C, for this alpha, this beta, and this gamma. So here's the base of the triangle AB. That's like my line L. Here's the point C, which is like the point P. And I can draw a line through C parallel to AB. So let me call this, say, DE. So DE is parallel to the base. Now, a theorem in Euclid says if you have 2 lines that are parallel, cut by a third line, alternate interior angles are equal. So here's this line BC that cuts the parallel lines AB and DE. This line, this angle beta and this angle up here are alternate interior angles, so they're equal. And similarly, the line AC cuts these 2 parallel lines, AB and DE. So this angle and this angle are alternate interior angles, and they're equal. So if you look at the sum of the 3 angles of the triangle, alpha, beta, and gamma, that's exactly the sum of these 3 angles on the top line, which make up a straight line, and the definition of two right angles are the sum of the angles that make up a line, equals two right angles. End of proof. So we use the parallel postulate to prove that the sum of the three interior angles of a triangle is 180 degrees, or a radian, or two right angles. There's another theorem in book 1, which says if you have any triangle, say A, B, C, if you extend one of the sides and look at this angle outside the triangle, this is an exterior angle. So if these angles are alpha, beta, and gamma, there's a theorem in Euclid, which is worked out as well in the text. Let's see. This is proposition 116 on page 41, which says the exterior angle of a triangle is greater than either of the two opposite interior angles. For this triangle, if this is the exterior angle, which are the two opposite interior angles? This is one and this is one. So this is saying that this exterior angle, let me just call it delta, say. So this angle delta is greater than alpha, and this angle delta is greater than gamma. That is, this is bigger than this, and it's also bigger than this. And there's an improvement of this theorem, which is very important. So using the parallel postulate, this is a much later theorem, one can prove that this angle delta is not just bigger than both of these, it's equal to the sum of them, angle of alpha plus the angle of gamma. So this angle is equal to the sum of these two angles. And once you know the sum of the angles of a triangle is two right angles, we can say the following. So here's the proof. If you look at beta plus gamma together, that's equal to two right angles, because it makes a straight angle. And if you add the sum of the three angles of the triangle, beta plus delta. Beta plus delta is two right angles. And the sum of the three right angles of a triangle, alpha plus beta plus gamma, is also equal to two right angles. So therefore, alpha plus beta plus gamma equals beta plus delta. Cancel the betas. You get the exterior angle delta is equal to the sum of alpha plus gamma, the other two interior angles. But we prove this using that the sum of the angles of a triangle is two right angles, and we prove that using the parallel postulate. Now, for 2,000 years, people professional and amateur mathematicians tried to deduce or prove the parallel postulate from the rest of geometry. And they all failed. They all failed, but people kept on trying because many people were convinced that the parallel postulate really should be deducible from the rest of geometry, and they wanted to be the person clever enough or lucky enough to find out how to do it. Until in the mid-19th century, people proved that everyone had failed because it wasn't true. That it was not possible to prove the parallel postulate from the rest of geometry. And what was proved was there exist consistent geometries of two other kinds, where first the sum of the three angles of a triangle is always less than 180 degrees. And there exist other geometries where the sum of the three angles of a triangle is always more than 180 degrees. And you could construct such a kind of geometry consistently. The names associated now, and it's one of these strange things. Independently, at roughly the same time, three different mathematicians proved this. There is the mathematician Gauss, who worked in what we would today call Germany, a mathematician Bolyai, who worked in Hungary, and a mathematician Lobachevsky, who worked in Russia. And at roughly the same time, all three were able to prove that you could not deduce the parallel postulate from the rest of Euclidean geometry, and you could construct a nice, consistent geometries where the parallel postulate didn't hold. Lobachevsky actually published his work first, but he published it in Russian, and no one read Russian in Europe, in Western Europe then, so no one knew what he did. Bolyai published his work in Hungarian, and it turned out that Gauss had already done the same thing and had written it all out in his notes, but he was afraid to publish it because he thought it would create a controversy and he wanted a quiet life. But independently, in the middle of the 19th century, these consistent geometries were constructed. Let me give you a rough example of a geometry where the sum of the angles of a triangle is bigger than 180 degrees. And there are no parallel lines. So if you have a line and a point not on the line, you can't draw a line through the point parallel to the given point. So let's take a sphere, a ball, the surface of a ball. So here we have a sphere. It has a center. If you intersect a plane through the sphere that goes through the center, it cuts out what's called a great circle. I mean, if you take a sphere and you cut it with a plane, like at this end, it's going to cut out a little circle. But this plane doesn't go through the center of the sphere. So this might be a little circle, but it's not a great circle. A great circle, all of the great circle, these are the lines. This is what we call a line on the sphere. Doesn't matter what its orientation is. These are all great circles. Like if you think of the Earth and you take the North Pole and the South Pole, you have these lines of longitude. So it's like you take a circle, you take a plane that cuts the sphere and goes through the North and the South poles, and you get the lines of longitude. That's what, so in this spherical geometry, let's call this spherical geometry, a line is a great circle. And in this geometry, parallel lines do not exist. Because if you get a basketball or something, take one great circle and then another great circle, and they're going to cross. Every two great circles intersect in 2 points, actually. All right? So there are no lines. If we took a circle that is a line and some point not on the line, there's no line through this point. So this is P and this is my line. There's a line is a great circle. There's no great circle through P that doesn't intersect L. So lines do not exist. And what about the sum of the angles of a triangle? So triangle, so we can talk about, let's say, here is part of a great circle, and here's part of a great circle. And you can look at the tangent lines where they meet, that's the angle. And here we have, so imagine this is like the North Pole, this is the South Pole on the Earth, and you take two lines through it. So where they meet at the North Pole, that's a right angle. And let's say this is the equator. So that's a great circle. And where these lines of longitude hit the equator, that's also a right angle. So this is a triangle. Just look at a globe, for example. Take two great circles, two longitudinal circles that meet at a right angle at the North Pole. And where they cross the equator, that segment of the equator is the third side of the triangle. This is a right angle, this is a right angle, this is the right angle, the way I've drawn it. It adds up to 3 right angles, more than 2. And if instead of taking a right angle at the North Pole, I take any angle, it still is the case that these 2 angles add up to 180 degrees. So the sum of the 3 angles of this triangle is this plus something more. So this is an example of a kind of geometry where many of the postulates of Euclid hold, but the parallel postulate is false. I mean, it's not the case. Another nice example, but somewhat more complicated, of a non-Euclidean. This is what is called. This is an example of what is called a non-Euclidean geometry. That's a geometry where the parallel postulate is false. Here's another example. In the XY plane, just look at the upper half plane. So this is like the upper half plane. So this is all points x, y, where the y coordinate is positive. And we can define a line in the upper half plane in two ways. There are two different kinds of lines. One is any line perpendicular to the x-axis. So it's only the line above the x-axis, but going out to infinity. That's one kind of line. And if we take any 2 points on the x-axis, take the midpoint, there's a unique semicircle joining those two lines, and we also call this a line. So in the upper half plane, we can define a line as being either a line perpendicular to the x-axis or a semicircle joining 2 points on the x-axis. And it turns out this gives a very nice geometry where the sum of the angles of a triangle is always less than 180 degrees. And here we have lots of parallel lines. For example, these are two lines and they're parallel. But in this geometry, if you take any line and any point P not on the line, instead of there being one and only one line through P parallel to the given line, there are infinitely many lines through P parallel to the given line. So that's not another kind of non-Euclidean geometry. The easiest one to think about is a kind of geometry on the surface of a sphere. And I put a couple of homework problems on spherical geometry just to give you a chance to think about it. Okay. All right, so that is what we're doing, what we've done in chapter 2. I remind you that next Monday is Lincoln's birthday, so there's no class. So our next class is a week from today, on February 14th, on Valentine's Day, actually. Wow. How better to celebrate Valentine's Day than with the history of mathematics? Okay. All right. Any questions before we quit for the day? Again, if you have other questions, I'm available tomorrow evening at 7. And if anyone has questions but can't come tomorrow evening, send me an email and I can arrange a time on Saturday, probably sometime in the afternoon, when I can also be on Zoom. But I'll set that up only if someone wants me to, and I'll announce it so anyone who wants to can log in, but only if I get some emails. But I'm happy to set up a question and answer session for Friday afternoon also. Right. Okay. If that's it for the morning,
Thank you, Professor.
See you next week.
See you next week. Thanks, Professor. Have a good day.
Thank you. You too.
Thank you, Professor.
Bye all.